Oh, hello. I attack a Leetcode problem like a convict. This is problem 1626, best team with no conflicts. Okay, you are the manager of a basketball team. For the upcoming tournament, you want to choose the team with the highest overall score. The score of the team is the sum of the score of all players in the team. Okay? So I want to just maximize my score by adding as many players as possible, right? But the basketball team is not allowed to have conflicts, okay? So conflict exists if a younger player has a strictly higher score than an older player. A conflict does not occur between players of the same age. Okay. So I can't add all the players, right? Because if I add some players, it could occur where, some younger player, player A, has a higher score than some older player, player B. And I guess there's seniority or something in this team, right? You could kind of imagine this happening in an actual team. In the context of software engineering, if you have a programmer with less experience getting paid more than a programmer with more experience, it may, add some turbulence to your team. So it might be appropriate to ensure that, people are paid correlated to their experience, and the older engineers are going to make more than the younger engineers. And you don't want to have an association where there's that kind of conflict. So same thing here, right? If the younger player has a higher score, they can't be put in the team because if there's an older player with a lower score than that younger player. Okay. Given two lists, scores and ages, where each scores I and ages I represents the score and the age of the I player. Okay, so these are parallel arrays. So I look at an index. For any index, that's the player. If I look at ages of that index, that tells me the age of that player at that index. And if I look at scores at that index, that tells me the score of that player at that index. Return the highest overall score of all basketball teams. Okay, so I could do a 2 to the n algorithm, right? And I could literally look at the power set, right? I could look at every single set of players that I could add, and I could look at their total score. Now, obviously, that is 2 to the n, and n can be 1,000. So 2 to the 1,000 is uncountable. I mean, it's countable, but it's unprocessable. It's not feasible. So we had to think of something a little bit better than that. But this is pretty short, right? I mean, less than 1,000, 10 to the 3. That indicates that there's probably not super efficient but optimal solution, right? So these constraints kind of indicate to me that maybe n squared would be fine, right? Because it's 1,000. That's 10 to the 3. So n squared would be 10 to the 3 times 10 to the 3, 10 to the 6. It'd be fine to... It's definitely a manageable number of operations, right? If you had an n squared algorithm that was 10 to the 6, that's small enough to be approachable. 10 to the 6 operations. I don't know why I made that so convoluted. Okay. So how do you approach this problem? Well, let's look at, okay, this example, we choose all the players, right? Because you could choose player 1 with score 1. So since the scores are just increasing and the ages are increasing in this problem, right? You can choose everybody. In this example, you have ages 2, 1, 2, 1, 4, 5, 6, 5. Okay, so let's look at this example. Okay. I just don't want to do this first one because it's a little simple, right? You can literally just add everybody, so there is no conflict. So what is that really going to indicate to us? It's not going to give us any additional intuition. So that's something to think about when you solve a problem, right? Which examples are going to actually provide you with some sort of intuition about the nature of the problem, and which ones are just going to waste time. Okay, so I'm going to draw these as nodes. So this is node 0, node 1, node 2, node 3, and 3, okay? And then there's the ages of these individuals, so I'll do that in red. See the ages, the age of the first person, he's age 2, 1, 2, and 1. I don't know what kind of sport has players that are 2 years old and 1 year old. Sounds heavily exploitive, but that's not there's no ethics in this problem. 4, 5, 6, and 5. Okay, so the scores are in blue, the ages of the players are in red. So if I look at each of these players and I say, let's just model this as a graph where, each person is this vertex, or these nodes, and we'll use edges to correspond to who can connect to who, whatever. And then think about from there what we can state about this problem. Okay, well, 2 can not connect. These 2 cannot connect, right? Because 0 is age 2 and this node is age 1, but it has a higher score, so they can't connect. These are the same age, so nodes of the same age can always connect because their scores don't matter. Right? So these people could both connect with each other. And for some reason I connected it to the wrong node because I'm losing my mind apparently. Okay. Now this person is also younger than this person, but has a higher score, so they can't connect. Okay, 1 is age 1. This person is older and has a greater score, so they can connect. Right? And then these 2 are the same age and they also have the same score, so they can definitely connect. Okay. All right, I don't need to look at these ones again because I've already asked the question. So here, 2, can 2 connect to 3? Well, it's older and it has a higher score, so yes, they can connect. Okay. So to find all those connections would take n squared time, right? Because I'd have to look at each node and then look at all the other nodes it could connect to. So for each node, I have to look at all the other nodes, right? So for n nodes, for each of those n nodes, I have to look at n minus 1 other nodes, so that's n squared. So does this problem just become finding the kind of maximum path within the system, right? Because if I can connect to one person, does that mean I can connect to the next person and so on and so forth? Well, sort of, right? The problem is, well, there's, I guess the easiest way to look at this problem would be like the longest increasing sum, right? Or the longest increasing sequence, right? And the sequence goes in the order of the ages, right? Because what I want is I want to add people of increasing ages. So I want to add people of increasing ages, right? Well, really I want to add people in non-decreasing ages, which is the same thing as kind of like thinking about this in terms of increasing, right? Non-decreasing, because I can add someone with age 4. So if I add people in terms of non-decreasing ages, there has to also be increasing. I'll do it in blue because I did the ages in blue. Increasing scores. Right, so this problem is very similar to longest increasing subsequence, right? Because what I do is if I look at people in terms of the age increasing, the scores have to be increasing, right? Because when I add someone of an additional age, right, if I add someone of a subsequent age that's larger, then the score needs to be larger, right? Because the only way person A and person B, right, if I have person A and person B and person C and person D, and they're all of unique ages, right? So this person is age A, and this person is age A plus 1, and this is person age A plus 2, and this person A plus 3, right? The only way A can be with B is if the score of A is less than B, right? The only way that B can be with C is with the score of B is less than C. Now, in this problem, if it's the case that the score of A is less than the score of B, then these people can connect to each other, right? Now, if the score of B is less than the score of C, then the score of C is also less than the score of B. So if something can connect to B directly, then they can connect to C, right? So it's like a longest increasing subsequence problem if you think about it in terms of the people's ages, right? If I sort this system in terms of ages, right? So I have people like this, A, B, C, D, E, F, G, H, whatever. I have these people, and I've sorted it such that everybody to my left has a less age. So if I look at E, all the ages of the people to my left are younger than me. So if they're all younger than me, that means if their score is less than me, then I can connect to them. And what I should do is just connect myself to the maximum score that I can get from adding to a previous person, right? So if connecting to C results in the largest score, then I would connect to C. If connecting to D results in the largest score and I can connect to D, then I will connect to D. So then when I get to a subsequent node like H, I would do the same thing and look at everything before me and try to find the node that would give me the maximum score if I connect to them. Right, so I'm just playing this game of longest increasing subsequence, right? I'm just trying to find the appropriate node such that when I connect to that node, it'll maximize my score. Right, so if I sort them in sorts of in terms of their age, then it's easy to process that information, right? If I looked at this problem again, right, because with this it's hard to say who I can connect to what, but if I sort them in terms of age, then I have what? It becomes an easier problem. You'll see how it's a longest increasing subsequence problem. So we'll do 1, and then 3, and then 0, and then 2. And then let's draw their ages again. So this person has age 1, age 1, age 2, age 2. And they have scores 0, 1, 5, 3, 5, 0, 4, 2, 6. Okay, so if we look at this problem again in terms of who you can connect to, it also becomes easier because you just look at the previous, like the only people you can connect to if you want to look at people that have a less age than you are the people with a lower score or an equal score if you're the same age, right? So 5 can connect to 1 because, 3, this node can connect to 1 because they have the same age. Okay, I look at 0 and I say, okay, who can 0 connect to? Well, 0 has age 4, so 2, so it can connect to everyone before it, but only the people have a lower age. Well, this person doesn't have has a lower score. This person doesn't have a lower score. This person doesn't have a lower score. I cannot connect to either of them. I look at this node has score 6. All the people to the left of have a lower score, so all these people can connect to it. And you can already notice that this problem looks much simpler now, right? And the cool thing here, right, is you could just do a DP solution where you keep track for each node, the maximum score you can get for something ending at that node, and then you just play that game going forward, right? So what you would do here is you'd say, okay, for every single node initially, right, the initial, I guess, score you could get is 5, 5, 4, and 6. Since 3 can connect to 1, it can get that score as well. So it would get 10. This can't connect to anything, so it stays at 4. And then since this thing can connect to everything, this last node 2, it would just connect itself to whatever maximizes, right? It could connect itself to 0, but it would only provide it with 4 additional. It could connect itself with 3, it could get 10 additional, or it could connect itself directly with 1, it would only get 5 additional. So the optimal solution is to choose this 10, and then you get a total of 16 here, right? So there's a DP solution where you just sort it based on age, right? And then you just do the longest increasing subsequence, right? Because that's what this comes down to, right? I connect longest non-decreasing subsequence, right? Because what I'm really doing is I'm just adding up the subsequence values that I can look at, right? I'm looking at, because you're given all the scores with the ages, but it's not necessarily sorted, right? So everything could be all over the place, but if you sort it in terms of age, it just becomes the longest non-decreasing subsequence problem. Now, if anyone's watching this and they already know the solution, there's one issue that I haven't addressed, and I will in a moment, but I guess the last thing, I guess I'll just address it now. I was going to do it a different way. But, for example, it is the longest non-decreasing subsequence problem, but let's think of one example which can really throw a wrench in this whole deal, okay? Let's say we have this first person, and their age is 6. So we'll do age in red again. Then we have this next person. Imagine we've already sorted it, okay? and their age is also 6. And then we have this last person, and their age is 12. Just choosing increasing, non-decreasing, I'm just choosing numbers here. Let's just say this is an example I thought of to prove a point. Okay? And these people have score 25, 2, and 6. Whatever. Or let's make everything all unique numbers so it's easier to not get confused about what's going on. Okay, so if we ran through this problem, right? So they already are sorted in terms of age, right? 6, 6, and 12. So that's good. If we ran through this problem, what would happen? Well, if we did the DP thing again, so each of them would start with the score that they can get, right? And then going forward, you would say, okay, although these scores are not the same, these two can connect, right? Because they're the same age. So there's a link going here. And then you could say, okay, this is actually 27 because I can add in the score of the person that I can connect to. And then when you go to 7 here, or to 2 here, it can connect to this one, right? But it can't connect to 6 because 6 has a higher score, right? It goes from 25 to 7, so it can't connect to this one. But since it can connect to this one, right, 2 can connect to 1 here, you might argue, okay, well then I can get these 27 points, and 27 plus 7 is 34, right? So I can get 34 points here. Is that correct? Well, no, right? Because I got 25 points, right? This 34 points comes from adding this 25 to 27 plus 4 plus 3, 34, right? Points. But that's not actually what's occurring in the system, right? I can't use all 3 of these people together. And why is that? Well, I can't use all 3 because what my end game is basically saying is that I'm going to use person 0, person 1, and person 2. But person 2 and person 0 can't be used together. So this longest non-decreasing subsequence doesn't work because there can be conflicts, right? When we think of conflicts as being someone having a score that's greater than our own or less than or it's not less than our own. If a person before us has a score less than our own, it should be a conflict. But since these people have the same age, it adds a kind of additional component to this problem, right? Additional aspect because, you know, I'm supposed to have a strictly higher score than everybody to my left, right? That I can connect to. And the idea is why that works is because if I can connect to someone to my left, that should mean that I can connect to everybody to their left, right? But the issue is, and this problem is that if they're the same age, the people to my left, although I might be able to connect to someone to my left, I may not be able to connect to someone to their left. Right? Because the kind of, what's that word called? I already forgot what a word is that I learned in college. Invariant. Sorry. So the invariant in the longest increasing subsequence is that longest increasing subsequence invariant, and that you're using dynamic programming for, is that if I can connect to someone to my left, then I should be able to connect to any person to their left. To the left of the person that I'm connecting to, right? The idea is in this problem, right? If I can connect to 3, if 2 can connect to 3, then that means I should be able to connect to everything that's to the left of 3 that 3 can connect to, right? Because I'm just building on top of the solution that already exists, right? If I have people that are in a row like this, right? I don't know what I'm doing here. Why am I doing this? Right? And if I ask someone to my left, hey, I'm taller than you, okay? So whoever you're taller than to your left, I'm also taller than, right? If I'm taller than you, then anyone you're taller than, I'm also taller than, right? So this person says, oh, well, I'm taller than this person. So that means I'm taller than two people, right? So whoever you're taller than to your left, I'm also taller than because I'm taller than you. So the number of people that I'm taller than is the number of people you're taller than plus one, right? For sure. I'm certainly that much taller. In terms of people to the left of you, if I want to do a longest increasing subsequence of people getting taller in a row, right? It turns out that I'm taller than all of these people, right? But if you want to do an order of people where they keep increasing in height, right? I would look at you and then I would say, okay, who are you taller than? Okay, there's these three people in a row that I can make a case about people getting taller in a row. If that makes sense. But that kind of, there's a wrench thrown in that whole idea here, right? Because although I have there's no conflict between me and this person to my left, right? Because I'm older than them and my score is higher. That doesn't necessarily mean that there isn't someone of their same age to their left who I can't match with. So how do we fix this invariant so that we can get back to this state where I can just look at someone to my left, and if my score is greater than their score, I can add them? Well, it really comes down to the way that these ages are added, right? So if we add all the ages sorted, we should also consider the score, because this problem goes away if we just swap 0 and 1. Why did I do that? Ages. Right, if we swap 0 and 1, what you'll notice is that I can't do very simple things. It's supposed to be blue. What am I doing? 25 and 2. Okay. So now if we look at this problem where we've also swapped with respect to score. Well, now watch what happens. It's going to give us the appropriate problem. So this has a higher score than everything to its has a higher age than everything to its left. And if anything to its left has the same age, it's going to have the same or a greater score, right? So I would say, okay, I can connect to you to my left because we have the same age and my score is greater by the way that this is designed. And then when I look at 12, well, I know I can't connect to 6 because it has a greater score. So this doesn't work. But then I can add this one to me, and then I can get the maximum score of 25, actually, right? Because the maximum score is just to use this one alone. But that's neither here nor there. But that's the idea. So why did sorting them also based on score eliminate this problem? Well, what happens now is, since we're adding the additional constraint that it's sorted by score, when I look at a new node and I look at previous nodes, right? It's always going to be the case that if I can connect to the previous node, I can connect to everything that comes that node can connect to, because if this thing is sorted based on score, so let's just do, I think the best way I can describe this is just using kind of a more mathematical related language. So if I can connect X to Y, right? And Y can connect to Z. Okay? So if Z can connect to Y and Y can connect to X, what does that mean about the relationship between Z and X? Well, first and foremost, these things have ages A, B, and C, and they have scores D, E, and F. Well, if B can connect to C, now these are sorted in terms of age, right? So the age A is less than or equal to B, which is less than or equal to C, right? Because they're sorted in terms of age. And since they're sorted in terms of scores as well, right? And since they can connect, well, since D can connect to E, then D is less than or equal to E. And since Y can connect to X, then Y is less than or equal to X. Or Y, D, Y, F. E is less than or equal to F. Right, well, since X can connect to Y, let's just assume for the sake of the problem that X is greater than Y. I mean, the age of, I should have done it the other way. C is greater than B, right? So if C is greater than B, and then let's assume that A equals B, right? So let's say these were both B. So both of these people, Z and Y, were both age B. Now, if D goes to E, that because they have the same age, well, E is going to be either greater than or equal to D, right? So if I can connect to E, then I can also connect to D, because the only way I can connect to E is if my score is greater than E. And since these things are sorted now, if I can connect to E, then I can definitely connect to D, because D is going to also be less than or equal to E. Right? So since these things are now sorted, since I can connect to E, then F is greater than E. And since I can connect to, and since these things, even if they're the same age, they're sorted, then if whoever I can connect to my left, I can connect to anyone to their left. So I just made this really complicated, and I apologize. But hopefully that makes a little bit of sense. Right? There's no longer the issue, because if I can connect to Y from X, and these things are sorted in score, well, the only way I can connect to Y from X is because I have a greater score. And since these things are sorted, then I can also connect to anything to the left. The problem before, right, was that since they weren't sorted in terms of score, there could be a greater score to the left that this could connect to, and I could make the argument, oh, since I can connect to this, I connect to anything to its left, but since they're not sorted in terms of score, then that would not necessarily be the case. So if you just sort them in terms of score, it eliminates that problem. I apologize for how convoluted I just made that. But with that, let's just go ahead and try to get into this problem. Okay, so what we're going to do is we're going to get the ages, the appropriate ages, and we're going to sort them in terms of age and score. So we'll look at each index, and then we'll sort it first based on the age of that index, and then on the score of that index. I'll just do it all down here so it's a little bit easier to see and I don't have to move stuff around. Okay. So now we have all the ages sorted, right? So if we print ages index here for this first problem case, it's going to give us an error because we didn't return anything, but it'll hopefully give us a printout. All right, so these are all in increasing ages and increasing scores. So maybe let's do the problem that we were using as an example. Okay. So it's 1, 3, 0, and 2. And then if you remember from our problem here, right, 1, 3, 0, 2. So those were the people in order, right, because the index is the person itself. So that's the order of the people that we should process. Okay. And then now we're just going to do the dynamic programming. So we're going to look at each node. We're going to look at everybody that comes before them. Everybody that comes before them, they can connect to if their score is lower. So we'll look at each age index in ages index. Okay, how are we going to do this? So each person, so there's a person, So there's the index inside the array of that person, and then there's the actual person. We'll enumerate this. This is going to get messy. I can already tell. All right, we need to create a dynamic programming array, which is just going to be, we'll just set it to 0. It's fine. times length of ages. Okay, and then we'll say, well, D at this index, or no, D for this person is the maximum score. So it's going to be the score that you can get from using this person, right? Because I can always use the score from the person in that system. And then the max score I can get from connecting myself to someone before me, right? Because if I can connect to someone before me, I can connect to everybody that they can connect to prior to them. So I'll just add them in. So I'll look at each person that comes before me in terms of age. So what would that mean? I would look at the D of that person, that younger person, because it's, so I look at each younger person that comes before me, or there's someone of the same age that has someone who comes before me with someone that's younger than me with a lower score, or someone that's the same age as me. So for younger person in, oh no, that means I need this system. People equals this. I'm sorry, people. We don't need to enumerate this then. I think you don't want to do that. We'll enumerate it on the next line. So you try to get cute, and then you end up making your solution more difficult. Okay, we'll look at each person. Say D of this person equals the max for each young person. We'll just call them Y, P, and P because it's getting... So in people, the people up to the current person that you're looking at. Ugh. And then the default value is 0 if you can't find anybody, because we're going to filter based on what? So we can add ourselves to that person if what? If the score of that person is strictly less than our score, or the age of that person equals the age of the current person. Right? So the age of the person that we're looking at and the person to our left, we can attach to them if that's also the case. And at the end, we just return the maximum score we can get from looking at any pairs of people. All right. Those can technically be on one line. Let's just submit that before we try to get too cute here. Ooh. So this says 1. All right, what did I do wrong here? So I'm looking at all the people that are up to me. If their score is less than my score, or their age is equal to my age, because I can connect to anybody with the same age, and I can connect to anybody that has a lesser score. Increasing scores. So strange. What am I doing wrong here? I'm missing something simple. So everybody has the same scores. And is there 10 of them? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So apparently I can add all 10 of them. Wait, how can I add all 10 of them if they have the same score and they're all different ages? Oh, strictly higher. So they can have the same age. They can have the same score. That's fine. Strictly higher is an issue. I just heard my phone go off. Okay, let's submit that again. All right, cool. All right, there we go. And then we can technically make this a 3-line solution just to flex on our friends because we're so smart. Okay, and then what's the runtime in the space? Okay, for let's just say that n equals the length of age, which is also the length of scores, right? For time, well, we have to look at each score. Sorry, so we have to sort this system, so that's going to take n log n time, right? Because we have to sort to find the people in the order which we need to process people to solve this using dynamic programming. And then for each person, we have to look at everybody that comes before them, right? So for each person, you have to look at everyone that comes before them. That's scalable with n squared. So plus n squared. And then for space, well, we just need to create this dynamic programming array, right, to keep track of the score of each, the maximum score you can get ending at each person's age or whatever, looking at each person. So that's just n space. So with that, it's n log n plus n squared. This is going to outshine that. So it's going to be n squared time n space, much like, you know, a suboptimal approach of longest increasing subsequence or whatever. Okay. All right, guys. Sorry about the poor solution today. I keep saying that and it keeps happening. All right. Peace out.